Today we're going to be working on lesson 9.3, which is real world problems involving the coordinate plane. So still the same chapter, big idea you can copy down. And then the objective for today is to solve real world problems involving equations and a coordinate plane. So we're going to work with what we did in chapter 8 and this chapter over coordinate planes. Okay, you'll notice you have a vocabulary word here, linear graph, which is also known as a straight line graph. Okay, so a straight line graph would be one that goes in a certain direction, so either slopes from bottom left to top right, or it could even slope from top left to bottom right, but you can see it would be in a straight line. Okay, you guys know what line graphs are. You guys have graphed line graphs, and they usually go zigzagged or something like that, but this is a straight line graph. Okay, so we're going to look at the learn section actually on this one, just so that we can make sure we're doing the right things and learn the correct wording. So first, I need you to copy down the chart. So that's time, which is T hours, and then distance traveled. So you can just put distance, which would be D, and that's in miles. So that's just giving you the abbreviation. If you can't see it, this is in your book on page 62 again. And then the chart is 0, 0, and then 1, 40, 2, 80, and 3, 120, and 4, 160. Okay, so we're going to learn to graph an equation on a coordinate plane. Okay, so you can see this is the coordinate plane. You can see we have only quadrant 1 right here, because we're only in the positive numbers. Quadrant 2 would be over here, 3 would be down here, and 4 would be over here. So we're only working with quadrant 1. And if we read the problem on page 62, it says Angela is driving to the Raccoon River. The distance traveled, or D miles, after T hours is given by, and then they're giving us an equation of D equals 40 T. And we could check that to see if it works. So if we filled in 1 for the T, 1 times 40 is 40, and that works out to be the D. If I filled in 2, 40 times the 2, 40 times 2 is 80, and that's what the D is for distance here. And it should work for these two as well. That's why the equation works, and it gives us the data here. So this is just the data that represents my equation. And then my graph is just going to represent those values of data that match my equation as well. So it says to graph the relationship between D and T. It says to use 2 units on the horizontal axis to represent 1 hour. So that means that this right here is not 1. I should have 2 units here to represent 1. So that's 1, 2 units. So I need to renumber my graph. This should be 0. Or technically this is 0, and this would be 0 and 1 half. This would be 1. This would be 1 and 1 half. This would be 2. This would be 2 and 1 half, and then this would be 3. And then I have 3 and 1 half, and then the 8 would be 4. And then the 9 would be 4 and 1 half. So my x-axis is going across, and that says that it is representing 1 hour. So I have 2 units representing 1 hour, that checks, and another hour checks. Okay, so if I look up at my chart, which one of these two is representing hours, and I know that that's time, so I'm going to label this part of my graph as time, and it's going to be in hours. So I do need to have a label here and then I need to have a label over here. So if this was time from the chart, you can probably guess that the vertical axis, the y-axis, is going to be distance. So we're going to label this distance and then put miles in parentheses. So this is D, and then this one is T. Okay, so we know this is the x-axis. Okay, we have the independent variable is here. And we know this is the independent variable, number one from our equation. It's independent right here. So whatever we plug in here makes this variable change, the answer for this one. So if I plugged in 2 for the time, the D would change based on that. If I plugged in 5 for 5 hours, I'd multiply it times 40, and that would make this change. So that means this is the independent variable, and this is the dependent variable. It will change based on that. The independent variable always gets graphed on the x-axis. And then the dependent variable would always be on the y-axis. So we know it's dependent because it changes based on the independent variable. You can think of that as, so I always like to say we know that if this were the baby and this were the parent, whatever the parent does makes the baby change. So if the parent chooses not to change the baby's diaper, the baby will probably cry. Whereas if the parent is nice and changes the baby's diaper when it cries, the baby will stop crying. So whatever the parent does, who's maybe thought of as an independent person, will change what the dependent is doing based on that. So we know that's dependent because it changes its behavior based on what the independent one is doing. Okay, so now we're going to graph what our data is showing. So I have 0, 0. So that's going to be my first dot on my plot. And then I have 1 and 40. So the time is 1. And then, I don't have up to 40. So it looks like I need to renumber my vertical line, which the problem tells us that 2 units on the vertical axis should be 20. So that means this is 10. This would be 20. That would be 30, 40, 50, 60, 70, 80, 90. And notice that this still is at 0, 0. So I have 1, and then I'm going to go up to 40. And then 2 will be at 80. And then I'm going to connect those. And then I know 100 would be here, 110. So I could keep going. Obviously, I would need to on my normal paper, but this graph will cut off. So 3 and 110 would be about there probably for the straight line. And then 4 and 160 would probably be way up there just by the straight line, you can tell. Okay, and what the problem asks us, so once you have those plotted, it says for A, what type of graph is it? So we know it's a straight line graph, but I want the other word for that. And you should know from your vocabulary right here that it is a linear graph. And then B says, how far did Angela drive in 3.5 hours? So I would go to 3.5 and go up. And it's off of my graph, which is actually the thing that is good because it was going to teach you that, yes, I could probably plot it on the graph, but it won't always show you the exact answer. But your equation will. So I can fill out my equation, and I know the time that it's asking. It's asking for 3.5 hours. So I'm going to plug that into my equation, and I know how to solve that. I'd find out the distance, which is how far, by multiplying 40 times 3.5, or 3 5/10, which would be 140. And we know distance is in miles, so this would be 140 miles. And then C says, what is the speed at which Angela is driving? So I just need to take speed. So that would be distance divided by time. So distance, I just need to find one of them. So I could find 40 right here. And I could divide it by 1. To make sure, I'm going to take one that's not a 1 or a 0. I'm going to take the 80 for the distance and divide it by the 2 hours for the time. And 80 miles divided by 2 would be 40. And then it's miles per hour. And I could check it with another one. 120 divided by 3 is still 40 miles per hour. 160 divided by 4 is still 40 miles per hour. I'll give you a chance to catch up if you need to. And then D says Angela has driven for 4 hours. So that's a time again. So I might need this equation again of distance equals 40 times the time. Okay, so she's driven already for 4 hours. If she drives for another hour at this constant speed, how far will she drive in all? So I'm doing 4 plus another hour. So 4 plus 1 is 5 times the 40. And it says how far will she drive in all? So I just need to do 40 times 5, which is equal to 200. And again, we're talking about the distance. So the distance is in miles for your label. E says if Angela wants to drive at least 120 miles, how many hours will she need to drive? Okay, so I know my distance I have right here, and we want to drive at least that. How many hours would that take? So I'm going to do 40 of my equation. It's the T, their time. So I made 120, and then I just need to solve this for T. So I'm going to divide both sides by 40. So this would be 3 is less than or equal to T. And I want to get it so the T is on the left. So I can just switch this order here. So T, and then if 3 was less than, then T would be greater than or equal to 3. So if I plug that in and thought about this, if 40 was greater than or equal to 3, that would be 120, which would make this at least 120, which matches what the problem is asking for. So that it would be greater than or equal to. And then F says name the independent and dependent variables, which you should know from your problem. So T is the variable, and D is a variable, not time and distance, but T and D. So T right here for the time is the independent variable because it's on the x-axis, and it's independent, and this is when is changing based on that. And then D, the distance, is the dependent variable in this problem. And we'll pause the video and give you a second to process that. And when you're ready, we're going to turn to page 66 and work on number 3.